This is Aziz Khan, and we are in lecture 24 for basics of microwave propagation. So, as I said many times, that I will try to build upon what we learned. So, if you remember, then in the previous lecture, we learned something about refractivity index. So, now we will build over it. So, as you remember in the last video, we talked that the refractivity index is always greater than 1, and we try to talk about the reason. So now when you reach here, you should not read it like a normal. I mean, the idea or what I really want is that whenever you are reading something, you know that why it is being said, why it's like that. As we told you in the last lecture that the formula is that the vacuum one is always above, the other mediums go down, and vacuum one is the highest. So the refractive index always comes greater than unity. And also we said that the difference in the speed of light in different mediums, it's not huge. I mean, it's a small fraction of change. The light speed change in fractions only, and their fractions are very small, in the vicinity of 10 to the power minus 6. So this you will now, whatever we talked about in the last, you will be able to connect it here. That for the ease of computation, we come up with this formula. So for example, like if you remember the previous formula, for example, if the average ground refractive index is 1.000315. Now if you see this number is not very simple. It's not very complex as well, but it's not very simple. And if you have to, for example, there are some layers of, if you are working on some link and there are some layers of different refractivity indices, then if you have to count them or if you have to know about them in these kind of numbers, that okay, this layer is 1.000026, the other layer is 1.00045, the third layer is 1.00095, and you know this long numbers and all start from 1 and then 000. There are many zeros, sometimes you miss the zero. So what they do is that from this normal n, which is a refractivity index, they transform it to another value of n, which is easy to understand and easy to remember and easy to manage. And they use this formula. So if you put this formula, if you put this number on this formula, so what is happening is that first you remove the 1. So this was 1.000315. You remove the 1, so it is 0.00315. And then you multiplied it with exactly the same number of, like if you see here, these are 6 numbers after the decimal. So when you will multiply it for 6, then this decimal point will be gone and you will remain with only 315. So this number, this refractivity index, which is fine for any scientist or physicist so that he can work on it, but for the radio guys, because it's a very a bit of difficult number, so we call it as 315 n units. So we make it simple. Now for example, if you have 4 layers and you know that one layer is 315, the second layer is 320, the third layer is 345, then you know that it's a bit easy to understand. You know that the refractive index is increasing very easily. You can understand the numbers, and you then don't have to make any, like for example, the number is simple. I mean, it's 326 or 325 or 45 or 95. If this was a number with 1.000, you will always have to count that how many zeros are there, which number is larger, which number is smaller. So this has just make it easy for you to understand. Otherwise, we can say that this number is no difference from this number. I mean, this n units, they come directly from this number. It's a simple transformation that transform this number into this number. I mean, n units is not something by itself. We can say that it is nothing without refractive index. It's just a way to represent refractivity index, and that's why it's called radio refractivity. But this radio refractivity, as we talked in the first lecture as well, so that I just want you to know that I try to keep these connected. In the first video, we talked about the refractivity is dependent on the pressure and temperature and humidity and these kind of things. But now we will just learn that how it is related. So scientists, they have come up with this formula, and they see that if we have a region, if there's a homogeneous region, and we want to know the refractivity of this region, then it is simply interaction of the pressure, the temperature, and the humidity. That how much water vapor is in this area. So if you see here, N is equal to 77.6, and then you have pressure divided by temperature plus 3.732 into the power 5 multiplied by E is the humidity, the partial pressure of water vapors, divided by T square, temperature square. So P is the atmospheric pressure in millibars, T is absolute temperature in Kelvin. So it's the temperature is in Kelvin, not the normal temperature, not centigrade or Fahrenheit. It's a Kelvin temperature which is almost 300 something degrees above the normal temperature. You should learn, or you should know, that how you can convert any temperature in kelvins. And then E is the partial pressure due to water vapors. So like that's why we say that in the coastal areas we have some refractivity problems, because in coastal area what happens is that there's a sea, there's always a source of water present, and that source of water, because of any temperature change or any change between day and night, even, and at almost in day and nights there is always a difference. In day, because there is temperature, also there is a sun which is making a lot of water to evaporate, so the area become more humid. So in the daytime it's a bit humid, in the night time it's a bit less humid. So night and day have very high kind of differences. I mean, in the night the humidity is also low and the temperature is also low. Two things, they go down, so your refractivity also go down. But in the daytime, because temperature is also high and the humidity is also there, so there is a change always. So this value of n, but this value of n varies with altitude. This also we discussed, that if you go from a normal ground area to a hilly area, so when you go higher and higher, your temperature, your pressure, your humidity, everything goes down. So refractivity index, how we calculate and why it is go down on, like for example, when you go to the high area, what happens is, because the pressure, temperature, humidity, everything goes down, so this total value of n, it also changes a lot with height, and it is different in ground and different in height. And also for some areas, like as we discussed, like for example the coastal areas, it can be different in days and in nights as well. So now we know the reason why it is different. When we say that in some area it is different in day and nights, now you can by yourself also, you can at least you can know now, if you are living in a barren area where there is no water resource and temperature also don't fluctuate a lot. There are some areas where day and nights are not too much different. I mean, there should be some different, but not too much, and because there is no humidity, so the humidity factor is almost gone. So in that areas the refractivity also remains almost constant, even in day and nights and in different time of years as well. But like in some other areas where the difference in temperature, pressure, humidity is very frequent, and the area is very fragile in terms of humidity and temperature, then your refractivity also changes a lot. So those are the areas where you get a lot of anomalies, and your links, they get some kind of problems. So hopefully this will be giving you some foundation to understand the things, and in the coming videos we will build more over it. We will go further and further. We will learn that okay, how these are related to our actual links, and we will try to learn more and more. See you in my next video. Goodbye.